So today we're going to do two kind of really cool activities. So the first one is we're going to think about solubility, but from an entirely different perspective. So most of you are familiar with infrastructure and the ongoing water crisis. So examples that have been in the news um, are Flint, Michigan, and Jackson, Mississippi. But there are lots of scenarios where cities and towns face similar crises. So, an example of one that's in Monterey County, close to home, is San Lucas. So, for the last 10 years, they've had to drink bottled water because the water that's being piped in through their tap is not safe to drink. So you can actually go and take a look at the infrastructure report card that actually talks about different communities and their access to clean drinking water. But that's the overall context that we're going to start thinking about solubility with. So this is our quick refresh your recollection. I want you to think about a practical example of solubility, something that you have done this week that involves solubility. Um, an example that I can think of is we were cooking spinach and I dissolved a little bit of salt in the water as I was preparing to blanch the spinach. And that was because I wanted the salt to increase the temperature. That was my boiling point elevation, right? So I was dissolving the salt. So that's my example. Can you think of examples? What's an example of solubility?
I dissolved honey in hot water to help with my throat.
Ooh, can you say that one more time? My internet must have glitched. I missed it.
It could be my internet. I dissolved honey in hot water because I came down with a cold this week.
Oh, no, I'm sorry you have a cold, but honey and hot water is a perfect example of solubility, right? That's beautiful. Any other examples we can think of solubility? I remember when I was a kid, we would make rock candy, and we would do that where we would dissolve sugar in water to make a saturated solution. And then you would let it cool, and the sugar would recrystallize kind of in larger chunks. And if you controlled how slowly it cooled, you could build like crystals, which I remember was really cool. So we have a jargony definition, right? The maximum amount of substance that will dissolve in a given amount of solvent at a specific temperature. So maybe the three most important ideas here is that it's relative to the amount. And we often refer to the substance that's being dissolved as the solute, and what is doing the dissolving as the solvent. But maybe for our purposes, at a specific temperature is the most important idea here. So our solubility is always going to be related to temperature, and it's always going to be a specific combination. So sugar and water or honey and water. Um, that solute solvent combination is going to have a different solubility than, say, for example, maple syrup in water or sugar in water, right? All of those are different sweeteners. Um, but honey, right, is very viscous and has some unique properties that might be different, say, for example, than maple syrup or sugar. And then insolubility is the opposite property. So it's the inability of a solute to form a solution. Now, this is the really interesting space, and we're going to start exploring this through some calculations. But this idea of solubility is something that we can actually calculate relative to the concentration. So, before we go further, I feel like a visual model can be really helpful. So, the solution is the combination, right, of solute and solvent, where the solute is completely dissolved into the solvent, and that solution tends to be homogeneous. That's different than a situation where we have a suspension. Can you think of an example of a suspension? Something where it's droplets in solvent, but they're not completely dissolved? The example that comes to mind for me is salad dressing, right? So you could have a suspension of vinegar in oil, right? And you have some of it that, right, never goes into solution, right? So that would be a good example of a suspension. A supernatant is an example where you have a precipitate. So this is the solute crashing out of your solvent. But the supernatant is often what we refer to if, say, for example, you have some of your solute in solution and some of it precipitating out. So that visual hopefully helps us as we move forward and think about calculations. Okay, so what's going to determine solubility? It really has kind of four components that we're going to be concerned with for the purposes of this class. The composition of the solute and the solvent. So, for example, what kind of sugar it is, right? And right, whether the solvent is something that is hydrophilic, right, that loves water, or something maybe that's hydrophobic, something that doesn't like water. And right, the pH of those respective pieces. The other piece that we're going to think about is the presence of other dissolved substances. So this is a really important component to think about. Is there anything else in solution? Sometimes that can influence solubility too. And then the last two are the most common that, say, for example, you would probably hear about if you were learning about this, say, for example, in a general chemistry class, and that's going to be temperature and pressure. So this dependence on these factors really is because of the interactions between atoms or molecules or ions of substances, and then thermodynamic concepts like enthalpy and entropy. So we're going to explore those in a little bit more depth by looking at some really practical examples. Okay, so the first one we're going to take a look at is silver chloride. So silver chloride has a KSP, and this is the equilibrium constant for solubility, of 1.77 times 10 to the negative 10th. So when we're doing a calculation like this, one of the pieces that we're going to think about is how does this behave when it goes into water? So if I have AgCl and I put it into water, what's going to happen? Well, what do you think? What am I going to form? What's the result of putting AgCl into water?
Is it just a precipitate? It probably
Yeah.
doesn't.
So I'm going to get silver ions out. And those are going to be solubles. They're going to be aqueous. And then I'm going to get chloride ions out. And those are going to be aqueous. And then the reason we have a KSP is because AgCl is actually a solid when we put it into water. And so what we really want to know is how much of the AgCl stays as this compound and how much of it forms Ag plus and Cl minus. So you're spot on. We're really just thinking about, well, how much precipitate are we going to see? So the way that we answer that question is to calculate KSP. Now, in this case, we're given the KSP. That's 1.77 times 10 to the negative 10th. But what does that number actually represent? Well, we set KSP equal to the concentration of the ions that are formed. So it's going to be the concentration of Ag plus and the concentration of Cl minus. Now, that's a lot to write out in an annotated form. So because these Ag plus and Cl minus are in a 1-to-1 ratio, I'm going to simplify this. It's just going to be the solubility of one and the solubility of the other. And I can simplify that to just say S squared, where S in this case is my solubility. So if I wanted to figure out the solubility of Ag plus or the solubility of Cl minus, all I would do is set 1.77 times 10 to the negative 10 equal to s squared. So I would take the square root in order to get s. So s in this case is going to be equal to 1.33 times 10 to the negative 5. Can I have someone just double check that when they put that into their calculator, that's what they get?
Yes, that's what I
Sweet.
got.
Thank you. I always feel so much better when someone confirms my calculations. Okay, so we've got this number, but what does that actually mean? I mean, 1.33 times 10 to the negative 5, right? If I were to write that out, that's 0.0000133 molar. So that's moles per liter. Well, that means that I can put 0.000133 moles per liter of Ag plus into solution. And since this is a one-to-one relationship, it means I can put 0.000133 moles per liter of chloride into a solvent, in this case, water. That's the amount that it's going to dissolve. Now, is that a lot? It doesn't seem like a lot. Right? So AgCl doesn't necessarily have great solubility, right? Yes, it goes into solution, and yes, right, I can have Ag surrounded by water molecules, and yes, I can have chloride surrounded by water molecules. But if I put too much of my solid in, right, I'm not going to be able to solubilize all of it. Okay, so that's one example, right, where it's two ions. Well, what if it's not two ions? Instead, it's a different number of ions. So we're going to look at another example. We're going to calculate the molar solubility of tin hydroxide. So tin is an example of a metal that we actually have to be pretty careful about. And hydroxide is pretty basic. So let's think about this. So if we had Sn, and I know that tin has a +2 charge, that means if I have OH minus that has a single negative charge, I'm going to have two of those, because that's my +2. So in order to have an overall net neutral molecule, I need 2 hydroxides for every 1 tin. So that means that when I think about how this is going to behave in water, I'm going to have 1 SN2+ ion. It's going to be aqueous. And I'm going to have 2 hydroxide ions that are also going to be aqueous. Now here's the super cool part about this. We're going to use everything that we just did for the silver chloride for the KSP for tin, except now our KSP is equal to 5.45 times 10 to the negative 27th. And that's going to be equal to the concentration of SN2+ and the concentration of OH minus. But now this 2 that's in front actually has to also be an exponent. Now, there's a really critical piece to this that is the most common error that folks make when they're doing this calculation. So for every 1 SN, how many hydroxides do we have according to our equation, right, that's generating the product? So for every 1 SN2 plus, there are 2. So here we have to do 2S and we have to square it. So if we think about this overall, this is the same as saying S times, and this is 2 squared, so that's going to be 4. And then S squared. So it's the same as saying 4S cubed. Now, when you're doing this calculation in your calculator, there are 2 ways that you could do this. So you could say 5.45 times 10 to the negative 27th. And then we're going to divide by 4. And that's going to be equal to S cubed. Now, you can take the cube root, if you have that in your calculator, or it's the same thing, right? If you say 5.45 times 10 to the negative 27th. Now, in my calculator, I usually have to enter this with a parentheses here. And then I divide by 4. And if I raise all of this to the 1/3 power, that's the same as taking the cube root. So 2 different ways to enter that into your calculator, depending on the calculator that you have. So S is going to be equal to, in this case, 1.11 times 10 to the negative 9th. Now you'll notice that I always make sure to put the unit here because this square bracket means concentration. So when I'm calculating the solubility, the unit that I'm using is for concentration. So it's going to be capital M or moles per liter. All right, I want to pause for just a minute before we move on to our third example and ask for GOTS and needs. So what's something that you've got about these kinds of calculations? What do you think? What's something that makes sense to you and that you know you need to do?
I had forgotten how like the exponents work for some reason, and so that was kind of a nice refresher.
Ooh. Yep, such a good reminder. I always need the reminder myself. So whenever there's a coefficient in our balanced equation, it becomes the exponent. So that's a good refresher recollection. The other one I think is that this coefficient in front also has to show up in the concentration expression and get squared. And the reason for that is because of the 1 to 2 relationship in this case. So 1 tin for 2 hydroxides. And the reason why it actually gets squared in this case is because when we think about that solubility, a 1-to-1 relationship is different than a 1-to-2 relationship. And we're going to see the impact of enthalpy and enthalpy on that, of enthalpy and entropy on that in just a little bit. So that's a great guide. Any needs? Anything about this calculation? Well, first I should check. Do folks agree with the answer that we got for this calculation?
Yeah, I got the same thing.
Sweet. Okay. So any needs about doing this type of calculation in your calculator? Okay, I feel like we're in a good spot. We're going to do one more example, and that's the limit on the scope of this class. So we're going to take a look at iron hydroxide. So in this case, our situation is a little bit different, right? So this is Fe. And because there's the Roman numeral 3 here, I know that this is Fe3 plus, which means that the hydroxide, because it's OH minus, there have to be 3 of them. So this is going to be 3. Now this is a solid. If I were to put that into water and I wanted to know what would happen, let's take a look at that. So I would have Fe 3 plus. And then for my balanced equation, this is an aqueous ion. So I would have 3 OH minus. And that's also an aqueous ion. Okay, so let's think about then what's the impact of that on our KSP. So I want you to take a look at that KSP number. Oh my gosh, it's so small, right? So our KSP is 2.64 times 10 to the negative 39. And if we're building out our KSP expression, right, we know we're going to do a square bracket for the concentration of iron 3 plus. And then we're going to do a bracket for our hydroxide ion. And that's going to be raised to the 3rd power. And if we're simplifying this, and again, you could use S, you could use any other variable, but I think S is most convenient. So this would be S by itself, because for every one Fe3 plus OH minus 3, there's one Fe3 plus. And then here it would be 3S to the 3rd power. So if we're thinking about that, right, that's going to be the same thing as S. So 3 times 3 is 9, times another 3 is 27. So 27 S cubed. And so if we're thinking about that, then this is going to be 27. And if you recall, right, S to the 1 plus S to the 3rd is going to be S to the 4th. So when we're multiplying exponents, we always add them. So this is like S to the 1. So S to the 1 times 3S cubed is S to the 1 plus S to the 3rd, or 1 plus 3, which is 4. And then we have our 3 cubed, or 27, which comes in front. So this is an instance where I don't know if there is a calculator that has the direct input for the cube root. In my calculator, which is a TI-30, I have to divide by 27 on both sides. And then if I wanted to solve this for the resolution of the root, it would be 1 divided by 4. So then S would equal 9.94 times 10 to the negative 11, and that would be capital N. So I want to pause for a minute and just check in with folks. A, do you agree with the calculation?
Yep.
Sweet. And then if we think about gots and needs, does this third example kind of follow the pattern? Does it make sense to you why it's 27s to the fourth power?
Yeah, it makes sense.
Okay, cool. So delightful news for you is while there are more complicated um, ion pairings, the limit that you're going to see for this class is a total of a Van't Hoff of 4, or this example. So we'll either look at pairs like the AgCl, threes like the tin hydroxide example we did before this, or fours. We won't have anything more complex than that for the purposes of this class. Okay, so now that you know how to do the calculations, let's take a moment and we're going to think about the next piece of this. So one really common and practical application of this is in acid mine drainage. So many acid rock discharges also have elevated levels of toxic metals. So when someone's doing mining, there's drainage, and typically the drainage contains nickel and copper, sometimes even lower levels of trace and semi-metal ions such as lead, arsenic, aluminum, and manganese. So this acid mine drainage is actually quite an environmental concern. When the pH of the drainage is above 3, either because of contact with fresh water or neutralizing minerals, the previously soluble iron ions then precipitate, and they become this iron hydroxide, which is this kind of ugly yellow-orange solid. It's colloquially known as yellow boy, but the really interesting piece about this is that calculation that we just did of the iron hydroxide is literally the calculation that they do to determine, well, how much of that iron hydroxide is going to precipitate in the mine drainage. So, sorry, went too fast. This class looks at practical examples. So we don't have exams. This was an example from the previous semester when I taught this class, but we're going to talk about the community water project. So no exams for you, but we will be looking at some practice problems that I'll record. For now, we're going to go back and we're going to take a look at your pattern of inquiry. So give me 2 seconds to navigate back there. I should note that this Thursday is June 19th, which is a holiday for CSUMB. So I'm going to record some practice problems. Actually, what I'm going to record are the exam problems from the previous time this class was offered and work through those as some practical examples. You can work on those on your own at your convenience. They're not due. They're literally just going to be example problems that will be helpful for us. So you'll see me walk through these with the key. I'll record that and post it to our YouTube. You've got a reading quiz that's due next Monday. And so let's take a quick look at the problems that we're going to solve. So here's our practice exam type problems. And so far in this class, we've covered colligative properties, osmolarity and osmolality, tonicity and blood serum and ion levels, water activity, some hydrodynamic radius and hydration shells. And then today we're looking at solubility and KSP and water as a solvent. So each of these problems is going to be an example of an application of those concepts. So ammonia is the foundation for nitrogen as the fertilizer industry. It can be directly applied to the soil as a plant nutrient or converted to other types of nitrogen fertilizers. What's the boiling point elevation when we have 11.4 grams of ammonia dissolved in 200 grams of water and you're given the KB? So that's a problem that's very similar to the colligative properties calculations that we did previously. Let's take a look at number 2. So as an alternative to sodium chloride, potassium chloride is often used in household water softener units. So I don't know if you have a water softener in your apartment, but if you added potassium chloride and you dissolved it in exactly 2 liters of a water solution, what's the molarity? What would be the osmolarity of the solution? So that's an example of a calculation based on the type of problems that we did last week. We also looked at hypertonicity. So hypernatremia is a common challenge, say, for example, for triathletes, as is hyperglycemia. So we talked about normal serum osmolality ranges. Actually, let me see if I can make this a little bit bigger and it will make it easier to read. Oh yeah, that's so much better. And we have normal urine osmolality ranges. If you have someone who's hypertonic, what would you expect to see? And so this is a good example of applying knowledge in a specific context. And then you all had a reading associated with water activity. So why is it okay to store peanut butter that has a water activity of 0.7 in a cupboard, but cheese spread with a water activity of 0.95 should be stored in a refrigerator? So that's kind of making sense of that concept of water activity. And then the Stokes radius or Stokes-Einstein radius of a solute is actually the diffusion rate of the sphere, and that's related to the size of the solute. So it's not just the size of that solute, but also the solvent effects that come into play. So you could have a smaller ion with very strong hydration that could have a greater Stokes radius. And that's because the smaller ion drags more water molecules with it. So we're going to have you compare the hydration of a large ion compared to a smaller ion. And if you're like, ooh, how do I figure that out? I'm going to introduce you to an open education resource that you can use to find that. So actually, let's do that. I think most of you are familiar with this resource, but just in case you aren't, we're going to go here. And this is the CHEM E2. So you can find this. I'm going to put this in the chat just to make life easier for you all. But this is an OpenStax text. It's Chem2E. This is the segment that we're looking at for solubility. And what I'm going to have you do is read individually the first kind of 3 paragraphs or so. So it gets split a little bit, but this is the last piece of that. So let's take 5 minutes and just read this text, and then we'll come back together and talk about what you noticed as you read. So take 5 minutes and read the text from the learning objectives all the way down to this part where it says link to learning with the video. Okay. I want to show you a feature of the Chem2E text that I find super useful. So you can do a search. In this case, let's say I wanted to know about ion sizes. And on the left-hand side, it gives me, right, all sorts of options. So I'm really interested in the variation of ions and their radii. So this is a good example, right? So the radius, right? So these are the elements just by themselves. If I wanted to know about their atomic radii, right, this is the segment of the text that would talk about that. So I could use this, for example, if I wanted to compare a large ion to a small ion. So for example, S2 minus is a large ion, right? Whereas Al3 plus is a small ion, right? I could do that comparison for the Stokes radius using something like this. Okay, I want to come back to what we were just reading. I'd love to hear from you. What's something that you took away from reading this text on solubility?
I feel like probably for me, this was mostly just a refresher because I do remember learning about like saturation and unsaturation.
Yep, I agree, Sydney. I think this is a nice recap of hopefully, right, refreshing your recollection for general chemistry. The piece about this that I feel like I want to direct our attention to is we're going to start to think about the solutions of gases and liquids. And so this is a great segment that's going to talk about that. And if, say, for example, you think about, right, the oxygen mixture, say, for example, that a scuba diver has to use, or they sometimes use hyperbaric pressure chambers as treatment for certain types of diseases, that solubility of gas in a liquid is going to become really important. The other piece of this that I think is really interesting, so most folks think about like carbonation. That's a great example of a gas in a liquid and its relative solubility. So that's another example. But Henry's law is the calculation that I want to direct our attention to next. So the example here is the partial pressure of oxygen in water. So we have a specific temperature, we have the concentration of dissolved oxygen, and we have a partial pressure. So we're going to use Henry's law to figure out the solubility of oxygen when its partial pressure is 20.7 kilopascals. So Henry's law is going to give us the solubility of a gas, right? That's information that was provided in the problem in this case. And that's going to be directly proportional to the pressure of the gas that's above the solution, right? So because we know both Cg and Pg, then we can solve for K, right? And then we're going to use our K to solve for our solubility. So in this case, we're going to rearrange this expression. So K is equal to Cg divided by Pg. Both of these are pieces of information that were provided in the problem. So now that we know what K is, we can actually use K to find the solubility then at the lower pressure. So here we know Cg and we know K, and we're given a lower pressure. And so now we can calculate what that solubility would be at the lower pressure. So Henry's law is a great example of something that takes what we already know about solubility and now applies it into a slightly different context. Okay. Within this text, there's one more piece that I want us to take a look at. If you want a little bit more practice, there are some additional practice problems here for Henry's law. But I think this is a great example of an application of what we know about solubility. So most folks that are in the marine science program often learn how to dive as scuba divers. And so one of the things they have to be attentive to is decompression sickness or the bends. And that's the effect of the increased pressure of air that's exhaled when you're at a depth. So there's the pressure of the atmosphere, but then there's also the pressure of the water that's above them. And about 10 meters is equivalent to 1 atmosphere. So if you're 40 meters down, that's 4 atmospheres that you're contending with. And so we use Henry's law to be able to figure out how a diver has to ascend, or rather the slow speed at which the diver must ascend to prevent the expansion of the gas. And so there are really interesting research experiments that look at, well, what are the impacts on cells that are experiencing the pressure and the changes, and can you use those to help address decompression sickness? So I feel like that's a really cool practical example of the content that we're looking at. Okay, let me go back for a minute to our problems that we were solving. Okay, so the ones that are going to be closely related to what we talked about today are 6 and 7. So water in the US can contain natural calcium fluoride along with other calcium and magnesium salts. But fresh drinking water does not contain fluoride. So the ingestion of fluoride during the development of teeth reduces dental caries or cavities due to the uptake of fluoride by enamel. So you're going to calculate the KSP of calcium fluoride, and you're given its molar solubility. So in this case, you're going backwards, right? You're told what S is, and you're going to have to think about, well, how do I get KSP? And then the last problem is one that is going to ask you to kind of think about, well, what is the relationship between solvent and solutes? So water is often called the universal solvent because it has this ability of dissolving many different kinds of substances. So we want to know why the chemical composition of water makes it such an excellent solvent. So I'm going to have you write a claim, evidence, and reasoning statement where the claim is water is the universal solvent because it's capable of dissolving many substances. You're going to be responsible for coming up with the evidence and the reasoning. So think about 3 different examples of water acting as a solvent, and then the reasoning or the scientific principles for why water is an efficient solvent. So delightful news for you. I will work each of these problems and post the key on Thursday, since we don't actually have a meeting due to June 19th. So if you want to, these are great problems for you to practice on your own, and then check the key. And I will post both of those and make them available. Actually, let me fix that now. So these were the practice problems. And then I'll post the key on Thursday. So we don't have exams in this class, but I think working practice problems is always really helpful. So if you'd like some additional practice problems, I can make those available too. We do not have class on Thursday. Again, this is because of the June 19th holiday, but I will record and post the solutions to each of those problems. And if you would like, I'll also make available some additional practice problems. So before we head out today, I've got an exit ticket for us. This is for week 3. Oh, let me make sure that I post that and make it available. So the exit ticket this week is going to ask you to think about a couple of things. So, right, of the content we have covered so far, so if you want to think about that, let me fix this. What is one concept you are confident you know for the first 3 weeks? I made the intentional decision not to have exams because I thought the pattern of inquiry was more revealing. So I'd be curious to know from you, what is one concept that you are confident you know? What's one concept from the first 3 weeks that you know you'll benefit from revisiting? And then, is there anything we've learned so far that surprised you? So I'm going to be posting, and then of course there's always the anything else you would like me to know. So this is our exit ticket for this week. You can work on that anytime between now and next Monday. I'm going to post your scores for the first two patterns of inquiry this week. So if you have questions about those, you're always welcome to ask. So just as a quick refresher, the items that are due so far for you is the first pattern of inquiry and the first reading quiz. And then the second pattern of inquiry on concentration. And then we've got a reading quiz that will be due next Monday. And then the last piece that we are thinking about is our practice problems. So again, no formal exam one for you all. We're not doing exams for this class. We're just doing patterns of inquiry. But these are great practice problems that help give you a sense of the content that we've covered so far in the first 3 weeks of this class. Okay, last piece that I want to show you, which is just super cool. So in the text that we were taking a look at, there was a really cool example that had just a great visual that is related to this concept that we've been learning about solubility. So I think this visual of the precipitation of sodium acetate is just incredible. So we're going to pause for a minute. I'm going to play it twice. Tell me what you notice. Okay, I'm going to play it one more time. It happened so fast. Okay, so I'd love to hear from you. What did you notice as you watched that
The
reaction take place?
super saturated sank really quickly compared to the other one. And then also it said that it's exothermic.
Yep.
It didn't mention the other one, but I'm assuming it's not.
Yep. Yep. Well, it's going to have, right, the same exothermic. The only difference between the one on the left and the one on the right is the amount of water. So they're both going to be exothermic, but because there's less water on the right, you'll see that temperature rise faster. So they'll both rise in temperature, but the one on the right will see that temperature change occur more quickly.
Okay.
I thought it was really interesting to think about this. So did anyone catch in the beginning what it said it was being added to? This is a really key piece of, let me pause it. So a seed crystal of sodium acetate trihydrate is added to a super saturated solution of sodium acetate trihydrate. So let's think about that, right? If we break that down in terms of pieces of information, right? So sodium, that's Na plus, and then acetate, so, right, that's O minus, because it's like acetic acid, except it's been deprotonated, it's lost its proton. And then this is CH3. But notice, right, so this is the sodium piece, this is the acetate piece, but it says trihydrate. So that means that there are 3 water molecules that are associated with this compound. Where would those water molecules associate? Where would we expect to see them? There are a couple of places they could show up. Where do you think we would see them?
Would they be hydrogen bonding, like with
Yeah.
the double bonded O?
Yeah,
Yeah.
I realized I wasn't unmuted, but yeah, the H's would be bonding to the negative O.
Yeah, so we could orient the partial negative charge of the oxygen on water to the sodium. That's one option. Another option is we could take our acetate that has a negative charge and our water could associate here, right, where it's a hydrogen orienting towards the oxygen. So that's our hydrogen bond, but we could also have a hydrogen bond here. Again, to the hydrogen associated with the oxygen. So what they did was they added a seed crystal of sodium acetate trihydrate, so a small amount to a supersaturated solution. And what ends up happening is that the one that had a little bit more water, where you saw those needle formations, well, that's because there was more water to separate the packing of the sodium acetate. So that's why you see the needle formation where there's more spread. Whereas the one that's super saturated with less water is going to pack the sodium acetate more tightly because there's less water. Although there's still the presence of water because it's the trihydrate. So I think that's such a beautiful example of solubility and how as soon as you exceed supersaturation, you're going to start to see crystallization and or precipitation. Okay, so let me clear this. All right, so we will not have class on Thursday because of the June 19th holiday, but I will post a solution of me solving each of those practice exam problems, and that's your pattern of inquiry for this week. So we're going to solve problems related to the concepts we've covered in the first 3 weeks. I'll post a solution key of me solving those problems on Thursday to our YouTube channel, and then I will see you all next Tuesday. Any questions for you or from you for me?
The